Today we move on to the design of a trapezoidal notch canal fall. As the name suggests, the trapezoidal notch canal fall indicates that the canal water falls through a trapezoidal notch. So we have to design the dimensions of the notch and the size of the walls. So we directly move on to the problem. Design a canal drop of 2 meter with the following data. Hydraulic particulars of the canal above drop. Full supply discharge is equal to 4 meter cube per second. Bed width is equal to 6 meter. Bed level plus 10. Full supply depth is equal to 1.5 meter. FSL is equal to plus 11.5. Top of bank 2 meter wide at level plus 12.5. Half supply depth equal to 1 meter. B. Hydraulic particulars of canal below the drop. Full supply discharge is equal to 4 meter cube per second. Bed width is equal to 6 meter. Bed level plus 8. Full supply depth 1.5 meter. FSL plus 9.5. Top bank 2 meter wide at level plus 10.5. The ground level at the site of the work is plus 10. Good soil is available for the foundation at plus 8.5. The particulars of the trapezoidal notch, that is canal discharge is equal to 4 meter cube per second. FSL upstream is equal to 11.5. FSL downstream of drop is equal to plus 10. The first step is design of trapezoidal notch. Assume 2 notches. Discharge through each notch is equal to 2 meter cube per second. Full supply depth is equal to 1.5 meter. Half supply depth is equal to 1 meter. Discharge through trapezoidal notch is given by an empirical formula. Q is equal to 2.093 into d raised to 3 by 2 into L plus 0.4 ND, where L is the length of the notch, that is width of the sill. N is equal to 2 tan alpha, where alpha is the angle of inclination of the side of the notch to vertical. D is the depth of water. As shown in figure, L is the length of the notch, D is the depth of water, and alpha is the inclination of the side with the vertical. So for full supply conditions, Q is given as 2 meter cube per second and D equal to 1.5. For half supply conditions, Q is equal to 1 meter cube per second and D equal to 1 meter. Substituting the values of Q for the full supply conditions, we get an equation connecting L and N. Now substituting the value of Q and D for the half supply conditions, we get another value, another equation connecting L and N. So we have 2 equations and 2 unknowns. So with this we can evaluate the value of N and L. That is, N is equal to 0.211805 and L is equal to 0.393, that is approximately equal to 40 centimeter. Now with the value of N, we can calculate the value of alpha, that is 2 tan alpha is equal to 0.211805, or alpha is equal to 5 degree 45 minutes. So with these values, that is with the value of L, we can calculate the top width of the trapezium. That is, the value of L is 40 centimeter and you have the value of alpha as 5 degree 45 minutes. With these two values, we can calculate the top width, that is equal to 70 centimeter. The next step is length of the drop wall between abutments. The length of the drop wall is generally 7/8 of the bed width of the channel upstream of the drop and is never more than bed width of the downstream of drop. Hence, adopt the length of drop wall as 6 into 7/8 equal to 5.25, where 6 is the bed width of the channel upstream. The next step is step 3, profile of the drop wall. The thickness of the drop wall at sill is generally 15 to 30 centimeter wider than the length of notch pier, which is half D, where D is the depth of water flowing over the sill of the notch. The thickness of the drop wall may be fixed as d by 2 plus 0.15, that is 1.5 by 2 plus 0.15. Here 1.5 is the depth d, that is 0.75 plus 1.5, that is approximately equal to 90 centimeter, which is approximately equal to 1 meter. So adopt 1 meter as the thickness of the wall. Height of the drop wall, that is equal to x plus d1, which is equal to 0.9 dc into root h. Here x is the depth of water cushion to be provided in the downstream below the bed level of the downstream drop. D1 is the full supply depth of the channel downstream of the drop. DC is the depth of water flowing over the drop. H is the depth of drop, that is difference in full supply level of the channel upstream and downstream of drop. Here D1, that is full supply depth of channel downstream of drop, is equal to 1.5 meter. DC, that is the depth of water flowing over the drop, that is equal to 1.5 meter. H is the depth of drop, that is the canal fall or canal drop, that is equal to 2 meter. So x plus 1.5 is equal to 0.9 into 1.5 into root 2, or x is equal to 0.41, that is approximately equal to 40 centimeter. Hence, provide the water cushion at 40 centimeter below the downstream level of the channel. Generally, the base width of the drop wall may be about capital H plus small d into square root of 2.25 for masonry. Here, capital H is vertical height of the drop wall from sill to the apron, that is equal to 2 meter plus depth of the water cushion, that is 2 is the drop and 0.4 is the depth of the water cushion. Small d is equal to depth of water flowing over the drop of wall. Therefore, width of the drop wall at the foundation is equal to 2.4 plus 1.5 into root of 2.25, that is equal to 2.6. That is capital H is equal to height of drop plus water cushion, that is equal to 2 plus 0.4, that is equal to 2.4. So the figure shows the height of the drop wall. The size of the drop wall, that is thickness of the drop wall at top, is equal to 1 meter, and height of the drop wall is equal to 2.4. That is, the level at the sill level is plus 10 and the level at the bottom is plus 7.6. Now the water cushion provided is 0.4. The bottom level at the downstream is plus 8, so that we get a canal drop of 2 meter. So, and we get a water cushion of 0.4, that is plus 8 at the downstream, and the bottom of the wall is at a level of plus 7.6. Therefore, we get a water cushion of plus 0.4 or 40 centimeter. Now provide a foundation of 1 meter thick, that is the bottom of the foundation is given by plus 6.6. At the bottom of the bottom width of the wall is given by 2.6 meter.